Alright, so today we will start our new chapter, which is chapter 3. In this chapter we'll talk about the digital circuit for the first time, because so far we covered number system, so we have some idea about binary numbers, hex numbers, right? And we know how to convert it from decimal back to decimal, and also little math like addition, subtractions of different number system, which will be very useful in all the digital logic discussion. Now here in case of the digital circuit, certain things are quite different than the regular electric circuit. I know that some of you are familiar with electric circuit because you have taken some classes, you have some ideas that how the electric circuit look like. And in the electric circuit we always talk about current, voltage, resistance, right? We still have all of those here, but the digital circuit, the most important is the logic, because the digital circuit works on logic. So that's why instead of talking about current, voltage and resistance, we'll talk about the logic. And the most interesting part here is in most of the digital circuit, especially the one that you have in the computer, because the computer is a big digital circuit, you have at any point you have either voltage 0 or voltage 5. So anytime we have voltage 0, we call it logic 0, or anytime we have voltage 5, we call it logic 1. When we have 1 and 0, after that point everything is binary, because we know the binary number system, right? So everything in the binary number system is 0, 1, which is pretty similar to the digital logic. And that's why before even we start talking about the digital circuit, we learned how to write the binary numbers, how to do the additions, how to do the subtractions, because at the end of the day we don't talk about the voltage, we talk about the logic, which are zeros and ones. And every single place in the digital circuit you will always either have zeros or ones. 1 means voltage 5, 0 means voltage 0. But remember, after probably today we'll never talk about voltage, because it will be only the logic, because that's only the thing that matters in the digital circuit, because the digital circuit basically can do addition, can compare, can also do other operations, but in the form of additions. And all those additions and subtractions and other operations are done assuming that everything is binary, because we know how to do the binary additions. We have some idea about binary subtraction as well. Remember, we did the binary subtraction as using 2's complement method, right? And remember I mentioned that when we were using the 2's complement method, I mentioned that the 2's complement method is nothing but it's a kind of addition, but at the end you get the result of subtraction, because the computer can only do addition, and that's why it does the subtraction in the form of addition. Now this chapter will give you a much more better idea of digital circuit, which is probably good for anyone who is just starting to understand the digital circuit. Okay. Now in digital circuit, just like the components of the circuit, okay, like the register or the other components you see in the electric circuit, we have some logic gates. Okay, those logic gates basically do some operation on logic. Now what logic we have? All the binary numbers or all the binary bits. For an example, let's say digit 1 is a binary bit, digit 0 is a binary bit. Okay, So the first one we have here is called an inverter. Okay. It basically inverts the logic. Okay. So the inverter inverts the logic. Okay. Now what do I mean by invert? So first of all, you have to identify this symbol. This is a symbol because, you know, remember in the electric circuit what happens, everything has a schematic, right? For an example, how the resistor look like in reality is not how the resistor look like in electric circuit, right? But we know exactly which is resistor in the electric circuit, right? I'm saying the resistors, the battery cells, they have different symbols in the electric circuit. So similarly in the digital circuit we have the logic gates, and they have different symbols here. And all the logic gate does is it takes some input. Again, input means binary digits, either 0 or 1. Okay. So as I said, you always have either 0 or 1, nothing else. And a lot of time people call 0 is low, 1 is high, or sometimes you will see the 0 is false, 1 is true, because, you know, that's the way people, you know, when you have anything with two logic, they try to write it like this, 0, 1, or high, low, or true, false. Now the inverter is a logic gate which basically inverts the logic. This is also called a NOT operation. So as you see here, the A is the input and the X is the output here. So this is just one input, one output. And all it does is it just flip the bit. Look at the table here. This is called the truth table, okay? Every logic gate has a truth table. And that truth table basically represents the characteristics of that logic gate. Basically, if you just look at the truth table, you exactly know what the logic gate does. It basically flips it. So basically what happens, if you give 0 here, you get 1 at the output. If you give 1, you get 0. It just flips the bit. That's it. It's so simple. Remember, at this point, after this point, we'll be never talking about the voltage. We only know the logic, and the logics are zeros and ones, nothing else. Basically, that is where the binary number comes into the picture, and everything in computer, inside the digital devices, even in the cell phone and any other digital device, is nothing but zeros and ones. And from zeros and ones, we know exactly how to write the number using only zeros and ones, right? Because now we know that we can write every single number in binary, right? We can do addition, we can do other operations in binary as well, but in the form of addition. So, and also remember, there is a part of math which involves all these kind of logic operations, which are called Boolean operations, okay? That's why a lot of time you see the word Boolean. Anytime you see the Boolean, that means that works with the Boolean logic, which means the binary numbers, zeros and ones. And since that is a math, again, when anything, you know, math, you'll see some kind of expression there. You'll see equation there, right? So you'll see Boolean expressions. So for an example, for each of the gate and for each of their operation, we can always write their expression, okay? That means how the gate is working, we know it from the truth table, but instead of writing the truth table, you can also write it as an expression. That expression, you know, like what the expression means. Remember, think about the math. What is an expression? Where you have a couple of variables, right? And some operators like plus, minus, those things, okay? Now here, we have also some Boolean operators. But they are not like plus, minus. They're a little bit different because they are like this. For an example, since this is a NOT logic or inversion logic, okay? We have an inverter symbol or NOT symbol like this. Do you see this bar? That is an operator. That is called inverter. So this means what? The X is the output of the circuit, right? X is basically inversion of A. we can call it x equals to a bar or a prime. Prime is, there is a little, you just put a mark here. That's called a prime, because when you are writing in, let's say, computer, you probably cannot write a bar always, right? Unless you are in the Microsoft Office. I'm saying the Microsoft Word, you cannot write the bar, right? Let's say you are writing an expression in WordPad, or you are writing the expression in pause. You cannot write it in bar, right? That's why instead of writing the bar, we can write a prime. So that means inversion of a is the output of the circuit, which is x. So all we are writing is x equals to a prime. You see here where the x is coming? X is the output and a is the input. So that's how in any digital circuit or digital logic, three things are exactly the same thing. For an example, if you draw the circuit, or if you, let's say here, if you just show the gate, we exactly know what will be the truth table, what will be the expression. Or if you write the expression, we know exactly what will be the logic gate and what will be the truth table. Or if you just write the truth table, we can exactly figure it out what will be the digital circuit and what will be the expression. Remember, we are not ready yet, so that's why we don't understand it yet, but over the time you will see in the digital circuit, the circuit, truth table and expression, they are the same thing, so it doesn't matter how you write. I'm saying either one is okay. If you write expression, we understand what will be the circuit. If you write the truth table, we'll understand what will be the circuit. And if you write the circuit, we always understand what will be the truth table and what will be the expression. So the good side is, in digital circuit, every single circuit can be expressed as truth table or as an expression. And excitingly, inside the computer there is a very big digital circuit, but you can still write everything in one expression. That will be a huge long expression. But just like a mathematical expression, the only difference is that it looks like mathematical expression, but it's not. It's a Boolean expression, because all the variables here can take either zeros or ones. In mathematical expression, what happens? Let's say you have a mathematical expression x plus y. Now the x can take all the real numbers, let's say, all the fractions. Okay? Y can take, let's say, all the integers, like all the whole numbers, right? It can be anything. But in Boolean expression, the only difference is if you see an expression x plus y, x is a variable, Boolean variable, y is a Boolean variable, so they can only take either 0 or 1. Okay, and just like, remember, okay, let's move on, and then we'll probably talk again. So remember, here today we are just going to introduce with all the logic gates. So there are three logic gates which are called the basic logic gate. This is one of those. Okay, we just have three fundamental basic gates. Okay, the reason they are basic, they cannot be created by some other basic gates. Okay, now let's look at next one. Okay, before we go to the next one, let's look a little bit about their waveforms, because remember, we always want to talk about the waveforms. You probably know the waveforms from electric circuit class, but here you will always look at the waveforms just like the pulse. Do you see the waveform of the A? So we are assuming this is a waveform of the A. Let's say this is given. Okay. Now remember, anytime if you talk about the waveform in digital circuit, it will always look like this, because in the waveform what happens? You will either see 0 or 1, because this level is 0 and this level is 1. So what we are showing here is, let's say it was 0 at some point, and then you change it to 1. It was 1 for a while, you change it to 0 again. It was 0 again, and then 1. You see what I'm saying? So it will be either flipping between zeros and 1, nothing else, because digital logic is always between zeros and ones. Okay. Now let's say this wave is given to us. Somebody said, I have the A. I know exactly how because if you go to the lab, I'm sure you have seen it, or some of you probably will be seeing it in this class. you can artificially generate the waveforms, right? You can, I'm saying, there is a signal generator, right? Remember, there is a device called signal generator, not the oscilloscope. There is another one which is called signal generator. It basically creates the signals, and if you want to test some device, or you want to, let's say, give some input to some device, you can use it, and then you can give the input to that device. So using that, let's say you just generated this waveform, okay, and you give it to some inverter. Now the question is, A is given, what will be X? Opposite, right? So let's try to draw it then. Look at the X. Do you see the X? It's exactly flipped, right? Whenever the A was 0, it is 1. And whenever it is 1, X was 0. And that's it. It's so simple, right? So we will try to understand the waveform as well for each and every logic gate we are discussing, okay? Alright, so these are the inverters, and also this will give you an idea. Remember when you do the 2's complement, this is just an example. When you do the 2's complement, what do you do? At the 2's complement subtraction, remember? What do you do at the first? At the first step, you flip all the numbers, right? So this is exactly how in the binary, in the digital circuit it is flipped, because you need a bunch of inverters, and you see all the input blips are flipped, right? So that's how exactly it is done in the electric circuit. But we'll come back here later. So this was an example. The next basic gate here is an AND gate. Remember, we always want to identify the symbol, okay? Symbols are so important in this class. These are new to us, but we also want to make sure that we understand the symbol. We can recognize it in the electric symbol. Automatically we recognize it soon, because you'll be doing a lot of pause quizzes. And in the pause quizzes, you'll be given some questions, and for sure you'll see those. Now, here, how many inputs you have in the AND gate? Look at the difference. 2 inputs, right? A and B. And output is always 1, right? Which is X. Alright. I'm talking about the logic gate. Each logic gate will always have one output. X is the output. Okay. Yeah, output doesn't matter how many inputs you will have. All logic gates will have only one output. Okay. Because at the end of the day, doesn't matter whether it's an input or output, it will be either zeros or ones, right? This is a digital circuit. Now, I said in all the logic gates, not even in the AND gate. All the logic gate, the output will be 1, or that will be one line only. Okay, but the input will be varying. Now here we have 2 inputs, and also we have a truth table here. Okay. Now what AND gate does? That might be the first question. Let's try to see whether we can find it. We can just tell it in a plain English sentence. AND gate gives you high or 1 when both of the inputs are high. AND gate gives you 1 or high when all the inputs are high. So that is the only time it will give you high. Now, before we go to the truth table, you see here we have written all the combinations of AB. How many combinations you have for AB? Do you think there can be more than 4? Are you sure? How can be more than 4? Because A and B either will be 0 or 1. How many combinations you can write for 2 inputs? How do we know it? There is a small way of identifying that. Let's say you have 3 inputs. Now we have 2 inputs, right? Let's say you have 3 inputs. How many combinations you probably can write? 3 inputs. So there is a small formula for that. It's not a formula, it's too easy, because all you need to do is this. All you need to do is 2 times number of input. Okay, so if it is 2, if there are 3 inputs, so the combination will be 8, right? And also there is an interesting part. If you look at here, there were 2 inputs, there were 4 lines, right? Because this is coming from 2 square. And also if you look at carefully, think about this. The first number is 0 in binary, right? Second one is what? 1, 2, binary 3. So when there are 4 inputs, it's basically 0 to 3. When there will be 8 inputs, because when you have 3 inputs, I'm sorry, not 8 inputs, I'm saying when you have 3 inputs, you'll have 8 lines, right? And all the combinations will be what? Just 0 to 7. If you just write 0 to 7, you should be done. Okay. Now let's go back to AND gate again. Remember the AND gate, what it does? It gives you high when all the inputs are high. Now let's look at the inputs and output. The first row, is this all high? No, right? So that's 0. How about the second one? It's also 0. How about the third one? How about the fourth one? Should be 1, right? That's exactly what it is. So look at this. So the plain English definition is exactly, you can see it here in the truth table. And also, as I said before, that every digital logic gate expression can be written as an expression. So here A and B we write using a dot symbol. Okay. Remember, in regular mathematics, dot is used for what? Multiplication. Okay. But here this is also called, surprisingly, this is also called Boolean multiplication. But that's AND. Okay. So, but for simplicity, you can ignore this dot. You can just write AB. So if you see somewhere, let's say is this, okay, x equals to AB, that means you know that A and B are ANDed. Okay, they are ANDed. Now how do you really work with this expression? Let's say for an example, somebody said A is 1. These are Boolean variables. They can be either 1 or 0. Okay. And let's say B is 0. Now, can you find what will be the solution of this x? Because this is how we solve Boolean equation or Boolean expression. Okay. Now let's plug A and B here. A is what? 1. B is 0. Dot 0. So what is 1 dot 0? That should be coming from here. Okay. Because we know that this is AND gate. Since 1 is 0, the inputs are different, you will get 0, right? I'm saying you will always get 1 when everything is 1. In case of AND, right? That is the logic of AND. You see what I'm saying? So this is the way we basically solve the Boolean expression. Well, there are plenty of expression, and you will get plenty of chances to do this. Let's get back to the waveforms. Let's say somebody gave us these 2 waveforms for A and B, because A and B are the inputs. Now, can we find what will be x? How the x will look like? Now remember, the x will be high only when A and B both are high, right? Both are high. Now let's look at carefully. Do you see the A and B, right? And you see exactly where they are high and where they are low. So look at this. We are blocking the areas with highs. So these yellows, do you see the yellow zones? These are the only blocks where A and B both are high. Do you agree? Look at the 3 blocks we just identified right now. These are the only places where both A and B are high. Do you see it? So that will be the place exactly where the x should be high, right? I think that's exactly the following the logic or truth table or or the expression. So over the time we'll learn exactly everything, how to write all of these from 1. Any questions so far? Let's look at the next one. I'll come back to here because I'm not trying to bombard you with plenty of information right now, just basic gates first. So this is the last basic gate we have, because as we said, we have only 3 basic gates. This is the OR gate, okay? Now, look at the symbol carefully, okay? So this is the symbol of the OR gate. Every symbol is a little bit different, so be careful about the symbols, and we should be able to identify the symbols anytime we see those in the in the digital circuit. Now again, there are 2 inputs, 1 output. The plain English purpose of the OR gate is, OR gate gives you high when either of the input is 1, either one. Now what will be the output in first row? 0, 0. Is 0, right? Because none of the input is high. How about the next one? That should be high, right? Because one of the input is high. Next one, it will be high also. How about the last one? It will be high also, because do you see the differences between the truth tables? I'm saying so far you have noticed, right? The truth tables are different. Every single logic gate has different truth tables. Either one will be, you know, something will be different for sure, because otherwise there is no reason of having that logic gate. So because the OR gate gives you high when one of the input, at least one of the input is high. So we have an expression for OR gate, and surprisingly, OR gate, the OR logic is represented by plus sign. So A plus B is basically means A or B in Boolean algebra. This kind of math is called Boolean algebra, okay? Because we write the mathematical expression, but they look same, but they are not, because the variables are Boolean variables. They can take only zeros and ones, and also for something else like this. Let's say with this expression somebody gave me this. Let's say let me tell you this. Let's say somebody said A is 1, B is 1, and what will be the A plus B then? Okay, remember in the Boolean algebra. So I just plug 1 here, and I also plug 1 here. So now this is A equals to X equals to 1 plus 1. What will be the output? Don't show it to your math teacher, okay? Because they will think we don't know math, okay? Because the 1 plus 1 is 1 in this class, not 2. So remember, because again we are talking about the logic. So 1 plus 1 is 1, not 1 plus 1 is not 2. Because all of these are basically logics. Now, again, the waveforms. Let's say somebody gave us this waveform, okay? Remember, these we have to identify the regions where either of the input is high. Let's identify those. Look at the blocks carefully. Unfortunately, the blocks are yellow. Do you see it yellow? So do you see the yellow blocks? There are 3 yellow blocks we have where either of the input is high. Look at carefully. Either one is high. Look at these blocks. Because, you know, here, this is one, here, both of these ones, here. So, you know, but the blocks where you have whites, in those blocks, white blocks, none of the inputs are high. Right? Probably it's easy to identify the white ones, because in the white ones, everything is low. So the output is low as well. Okay, because what is the logic behind? Because the OR gate gives you high when any of the input is high, right? Any of the input, either A or B. So that's why we identified the yellow blocks where any of A or B or both is or high. So this is all about the basic gates. Let's look at the next couple of important gates. Now remember, these are not basic gates because they are derived from the basic gates. We probably will talk about why they are not basic in future, but just for now we know that they are not basic gates. Now look at the symbol. Do you see the difference here? this just look like an AND gate, but with a bubble at the end. Do you see the bubbles? Now these bubbles are so important. Don't miss the bubbles, because if you just ignore the bubble, the gate will be different. Okay, because it just look like an AND gate, but there is a bubble at the end. Now the NAND gate gives you a low when all the inputs are high. Every time else it gives you low. Every time else it gives you high. So when all the inputs are high, which is this case, right? All the inputs are high, it will give you low. Otherwise, it will give you high then. So let's write it. Everything is high except the last one. Because whenever everything is high, it gives you low. How do you write it? It's very similar to AND, but there is a bar. AB bar. Okay? Bar is on the top of the board. Okay? Now remember, when you write it in let's say notepad or in pause, you cannot write this expression, right? I'm saying in the pause, you cannot write the top bar. So what you can do is, instead, I'll probably add it here in the slide. I'll add that. Instead, what you can do is, instead of writing AB whole bar, you can write this prime, whole prime. Because remember I said the prime is a replacement of bar. But how do you write the prime on the whole expression? You just put a whole bracket or parenthesis, then prime. That means the prime is applied on the both or whole expression. Okay. So this is how you are going to write it in pause. Because in pause you can write primes, but cannot write bar. That's the same thing. So, all right. So how about the waveform part? A and B are given. How do I find the waveforms? Remember, we have to identify the blocks where both of the inputs are high, right? So let's identify the blocks. Do you see these blocks where both of the inputs are high? Only in those places. Only in those places the input is low, right? As long as we know that logic is fine. And remember, we know the good news, right? Because we have all the tests open book. So you will always have the access to all this information. But don't wait until the test starts to study these materials, okay? Because in that case, test will be more exciting. Now, the NAND gate is called an universal gate. We'll talk about this later. Just at this point, just know that this is an universal gate, because every other gate logic can be implemented by NAND gates. So we'll come back to this point later, because there is a separate block of discussion on this. So I don't want to bombard you at this point. So we'll come back. Another gate, NOR. All the gates, you probably can see right now, all the gates are pretty much similar, because they have little bit different symbol, they have little bit difference in the definition, and that's why the truth table is a little bit different, expression is little bit different, waveforms are different, but everything works on their property or their characteristics, right? Now, what is NOR gate? The NOR gate produces a low if any of the input is high. First one, of course, high. But it will give you low anytime you have one input with high. I think every time it will give you 0 here, because there is a 1 here, there is a 1 here, there are 2 ones in the last one, so you will get zeros. And NOR gate is also pretty much close to OR gate, right? Except there is a bar on the top. But how do you write this expression in pause? You can just write A plus B whole prime, right? So the bracket A plus B and then whole prime. Because you can always write the primes. How about the waveforms? Remember, it gives you low anytime you have 1. So we have to identify every zones or regions with one of the input 1 high. So these are the 3 blocks, right, where either of the input is high. So these will be the places where the yellow blocks will be the places where your output is going to be low. places. This is exactly what you expect, right? So the output is low in those places. So we are almost close to the end because there are only two logic gates left, this one and the next one. But it's pretty much same, and after that we'll start the practice session and there will be 5 quizzes on this. Will not be done by today for sure, but we'll be practicing in next couple of classes just to make sure we understand all the concepts, make sure we know everything, and then there will be a test which is on whatever we have learned so far from the number system and from the logic gate side. But we need a lot of practice for those to make sure we understand, because there will be plenty of different things. We have to answer questions from the truth table side, and also from whether we can understand the waveforms. So you saw the waveform. So there will be a variance, because here all the gates we have two inputs, but the gate can be 3 input as well, but the logic is still same. We'll come back to those points. Now this is called exclusive OR gate, or some people call it XOR gate. Do you see this? The gate is very close to OR gate. There are 2 lines here. Do you see there are 2 band lines here? There are 2. Now, so that's how logically this is also close to OR gate. Remember the OR gate. The OR gate was what? It gives you high when any of the input is high. This is pretty close to that. But the only difference is this. It gives you high when the inputs are different. Okay, look at this. It's not different, right? Both of the inputs are 0, so it's not high. Both of the inputs are different, right? Input should be different. Still it is different, so this is high. But now it is not different. So the last row is different here. Remember, in case of the basic OR gate, this was high. But now, as I said, as we know, the definition is it gives you high when the inputs are different. Middle 2 rows. Okay, and there is exciting symbol here waiting. So, we write it A prime B plus AB prime, or sometimes there is a symbol. I think it's a little bit messed up because of orientation. This circle should be here. I'll move it before I upload it again. The symbol is this. That's called exclusive OR, plus with a circle around. This is the symbol of the exclusive OR. This circle is moved here. This should be here. So the circle should be here. So that's the exclusive OR, because it's very close to OR. So that's why, remember, the OR is plus, right? So, and there is a circle around. I'll move it before I upload it again. So here again the waveform question. A and B are the input. What you are trying to identify, you will be identifying the zones where the inputs are different. Right? Let's see whether we can find this. Look at these places. Look at all the yellow blocks. We have like 6 yellow blocks here. In every yellow block, the inputs are different, right? Do you see it? Inputs are different. So one is 1, other one is 0, right? So these are the only blocks where the output is going to high. Going to be high, right? These are the yellow blocks at the places where your output X is going to be high, right? Because the inputs are different here. So exactly we have it. So look at how we have drawn the waveform. So those are the only places where your output is high, because those are the places where the inputs are different. So the one more gate, which is pretty much like exclusive NOR gate, which is basically the inversion of exclusive OR. The only logic difference here is these will give you high when inputs are same. It's just invert logic of exclusive OR. So this will give you high here because the input is same, right? Both of the inputs are same. Low, low, high. Do you see the difference? Because this is giving you the high when both of the inputs are same. And that's also pretty close here, but it's also moved. So the way we write it is dot and a circle. The circle is moved there. I'll push it here because probably some line was changed. And do you see the exclusive OR symbol? This is very close to exclusive OR, and there is a bubble at the end. The bubble is something which was not there in the exclusive OR gate, so that makes it exclusive NOR. Now, again the waveform question. So we will be identifying the zones where both of the inputs are same, right? Either both of the inputs are low or both of the inputs are high. Let's identify those blocks. Look at the blocks here, the yellow blocks. Every single yellow blocks, both of the inputs are either 0 or 1. Do you see it? All the blocks, yellow blocks. So these are the places where your X is going to be high, right? That's exactly what we expect, right? So that is what we have for the logic gate. Now, one of the exciting question might be that how this logic gate look like, because we have never seen the logic gate so far, right? All the logic gates basically come as IC, integrated circuit. I think some of you have seen the ICs, right? In all the the digital circuit, you see some of the ICs, black ICs, the plug-in. Now, interestingly, those ICs basically contains the logic gate. For an example, let's say this is an IC. For an example, all these are ICs basically. We just tried to pull some ICs for you so that you'll see how the logic gates are coming into the digital circuit, how they look like. Because we just so far look at their schematic, because schematic is not exactly how they look like in the real life. In the real life, they are all ICs, but they have different numbers. Just from their numbers, we know exactly what logic gate it is. Now, can you identify this gate? Let's go to a basic one. Let's say the first one. Can you identify this logic gate? What it is? That's the NAND gate, right? Now, look at this. 1, 2, 3 makes one NAND gate, because the 1 and 2 are input, and then 3 is output, right? And again, 4, 5, 6 makes another one, where 4 and 5 are input, 6 is the output. Similarly, 8, 9, 10 makes another NAND gate, where 9 and 10 are the input and 8 is the output. So you see here, so how about this? What is this? Inverter? You see the inverter here? So there are 6 inverters basically. What is this? NOR gate. How about this? 2 input AND. But look at this. There are some 3 input gates as well. This is the 3 input NOR gate. But still the logic is same. Whenever you have, let's say, 3 input AND gate, what will be the logic? The logic is all inputs should be high to have an high. So if you have 3 input, that means what? All the 3 inputs should be high to get an high in the output. So still the same definition applies. So, again, I just tried to show you a snapshot of all the ICs. When you will go to lab, or before we go to the lab, we'll be using, or we'll be looking at some of these ICs, and you'll be working with some of these ICs in the lab for sure. Not even all, but most of those. So, and all these ICs, they have a name of this. They belong to a same series. We just wrote 0002, but their original name is 7400. So the next one is 7402. So all those ICs start with a series name called 74. Okay, 7400. So after when you start going to lab, you will see, okay, 7411. We know exactly what that IC is. For an example. Or let's say 7402, we exactly know what that IC is. And also, before you even start working with that, we'll give you some kind of information like this. That's called a data sheet. In the data sheet, you will exactly know what pin is what, which pin is input, which pin is output. Just like here, exactly from here, you'll know exactly which is the output and what is the output and how you can make it work. We'll talk about those. These are the basic definitions that we have seen here. Again, I just tried to list all of the definitions in one place. Now we are ready for chapter 3 quiz. There are 5 sections of this quiz. Since you are done with the number system, you exactly see the first one, I think, right? But if you do the first one, you'll see second one, third one, fourth one, fifth one. Now, the first one is a little bit different than all the logic gates, because First one is a little bit basic about the digital circuit. So we'll be asking about basic digital circuit question. Starting from the second one, you will see more close questions to the logic gate, and the last one, which is 5, is absolutely on the waveforms. I think you'll be given a couple of waveforms and you have to decide how the output, even the output also. We'll be giving you, let's say, 3 inputs or 2 inputs and 1 output. Okay? Just looking at the input and output, you have to tell us, is this an AND gate? Is this an AND gate? That's what I'm saying? Because you know the definition, right? You know exactly how it should be changing based on the definition. So the slide is still there in the pause, so, but I'll probably update it and upload it, so you can always go back to slide, and also the lecture is recorded, so you can always go back to the lecture with the voice. Any question before we start the quiz? Now this is all about chapter 3, so this is the end of chapter 3. So the chapter 3 is extremely useful and important because this is the starting point of the course. And also after we are done with all these quizzes, the 5 quizzes here, and also we did all those number system, we'll be able to do all the sample test for test 1. Basically we'll be ready for sample test and test 1, okay? Because the test 1 will cover number system and chapter 3 only, okay? So, and also after this chapter, we'll have a pre-lab and then we'll be ready to go to the lab, because the first lab will be the lab 3, because we already did the lab 1 and 2, which are math. But the lab 3 will go to the lab and then we'll start working on the logic gates. We'll build circuit, we'll check their truth table, you know, and then chapter 4 again we'll be always talking with the logic gates for sure. Any question here? Okay, if not, then I'll stop the presentation here and then we'll go to the pause and